Okay, now let's look at PD controller. We saw that proportional control has some drawbacks. Now we want to use another term here and see if using that term we can compensate for some of these drawbacks of the proportional control. So PD control has an extra term here and says, you know what, your action shouldn't only proportionally depend on the error. It should also depend on the derivative of the error. What does that mean? Why would that give us any more power? Well, because derivative is the slope of a function. So if I take the derivative of the error, not only I have the value of it at this moment, I also can see the trend. I can see the slope of it. I can predict what's going to happen in the future. So my action can be dependent on the actual value of my error and also the way it is going. It's like we predict if we continue this way, what's going to happen in the future. So adding derivative control decreases or removes overshoot. That's what we want. That was the problem with proportional control. But now it has some problems. What's the problem of it? It slows down the response. Notice that derivative control does not care if your error is big. It doesn't care about the actual value of your error. It only reacts to the rate of change of error. So imagine if error value is 3,000 trillion, okay? But it's constant. What's the derivative of a constant value? It's just zero. So if you have a huge number and it's not moving, your derivative term isn't doing anything. But if you have a number that is small and it's increasing with a range of getting like with a range of 1 per second, the derivative of it would be 1. Okay, so as we talked, the effect of derivative control is that it increases, it decreases overshoot, which is what we want, and it increases the peak time, which means that this is high KD, and this is not the response we want. It slows down the response. We want a faster response. Let's see what happens to our servo motor of the previous example in the proportional control. So this is what we had. Recall that the response of proportional control was this. It was oscillatory when we used the proportional control, and the voltage here, the control action we used was smooth. Now using PD control, look at what happens. There's no overshoot. That's amazing. Adding derivative control lowers or removes the overshoot, but it slowed down the response. See, when we get to the final value, almost at 1.5, here it was at 1.1. So it slowed down the response. In addition, look at what happened here. I go one slide back. We had a smooth behavior. The control motor voltage control we were using would jump to 1 and then damp. Now it goes up to 5 with a spike. So if you're using we are talking about real systems, the actual equipment that is supposed to take the action might saturate, might not be able to do that. Your actuator might saturate. So another disadvantage of derivative is that if you have noise in your measurement data, it's really sensitive to it. In what we discussed right now, we assumed everything is perfect. We assumed there is no noise, and still we had these problems. Imagine if you have a noisy behavior. Imagine if you have a noisy measurement, which is the case in real life. Then the problem is that if you take the derivative of a noisy behavior, think about it. What's noise? Noise is very quick ups and downs in your signal, and that's what taking derivative is sensitive to. It sees those ripples and jumps up and down, and it amplifies them. So the derivative action loses its benefits when there is a random noise. The derivative action causes the measurement noise to be amplified, and it reflects that in your controller. So to stop that, if you have a noisy behavior, the solution is to use a filter, which in the lab we have studied that, right? If you have a noisy behavior, you use a low pass filter. So this is called chattering. Chattering is when you have ups and downs, you have these vibrations in your response. The control signal chatter is amplified when you have derivative gain. Okay, another problem is derivative kick. What's that? Imagine if I have this behavior. I have an input, this is my desired value, and my system is tracking it. And then my desired behavior or my reference signal jumps down. So it's positive and then negative steps. My my system is trying to track that. Now, this seems okay, right? This seems what we want to do. That this doesn't seem very complicated. Now think about what, from the point of view of a derivative gain, this problem is going to be seen. So we want to take the derivative of the error. What's the error? Error is the subtraction of the actual behavior from the desired behavior, right? So the error here is bigger, and then it gets smaller, 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 almost zero. And then at this point, it suddenly jumps into a bigger number. The derivative, seeing this behavior, an error value that jumps from zero to a big number, takes the derivative of that, and that is a spike, or as we call it, derivative kick. So in examples like this, when you have a behavior that you have, for example, a reference signal that is a pulse, and you're you're gonna see these jumps, and you're gonna have the kick. Rather than taking the derivative of the error, we can just take the derivative of the output. That would smoothen out the uh, controller value or the control signal, so we don't have the kicks. See these examples. So we talked about the servo system. If we have noise in our measurements, this is going to be our output. So the uh, it does have the behavior we want. It tracks the input, but look at this noise in the output. It's terrible. In addition, the control signal is also sensing that. Your control signal is also very, very, very noisy. If you use a filter, now it's much smoother. But the problem is that your filter now is adding to the overshoot. Okay, so the takeaways from the PD control is that PD control removes overshoot. And if you have noisy behavior, PD controller can be used if you use a filter. The drawbacks is that it can make the output and control signal noisy. And if you use a filter to mitigate that, it slows down the response and it might lead to overshoot. Let's have skill check. What's the drawback of derivative control when used in a physical system with sensors? Option A, can't be used together with proportional control. Option B, make the output response faster. And option C, can generate noisy signal when sensor measurement is not smooth. Which one is the drawback? Statement A is wrong. It states that we cannot use derivative control with proportional control. That is wrong. We can use proportional control and derivative control. Item B, make the output response faster. That's not what we mentioned as the drawback. And if it can make the output faster, that is not a drawback, that's a good thing. So item C is the response. It can generate noisy signal, that's a drawback of PD control, when sensor measurements are not smooth. Next question, what does the derivative control do when controlling something like a DC motor position on the angle of a robot joint? Does it decrease control signal that is needed? Does it make the response faster, or does it remove overshoot in the output? It does C, right? It removes the overshoot, but it doesn't do A or B. Okay, last is PI control. PI control is when we keep proportional control and an integral. So now, not only I say the input, the control signal depends on the proportionally to the error, I want it to also depend to the integral of the error. Why would I care about the integral of the error? Remember, proportional term sees this exact element, sees this exact moment, and reacts based on the value of error at this moment. Derivative is trying to predict the future, is trying to react to what is going to happen in the future. What does integral do? Integral looks at the past, right? Looks at the history. It's the area under the curve of the error. So why is that useful? For some systems, the PD control, with PD control, the output response has a steady state error. Imagine if you have a steady state error. Imagine if you are at a situation that there's an error and it's steady, so you're not removing that. The proportional behavior or proportional control sees it, but isn't going to change the value because it's a constant gain. The derivative doesn't see it because you have a constant value. The derivative is 0. But the integral would amplify the error the more you wait. So integral can see a constant value if you wait enough. It's going to make it bigger and bigger. The integral term adjusts the output based on accumulated error over time, and it is used to eliminate the steady state error. So let's see this example. We have a system. This is the system, and we have Kp equals to 0.5. If we give a step to the system without any Ki, my system is going to do this. My system is going to stop at 0.5, but the goal was to get to 1. So my system has a steady state error. If I try to increase Kp to 10 and 20, I'm gonna get rid of the steady state error, but as you can see, the more you increase Ki, you're gonna increase the overshoot. The response gets faster, but you increase the overshoot.